do is they wanted to actually verify, is light a wave, or is this just a random theory? And so this brings us to one of the most famous um, famous experiments of like physics. Cool. So if you remember back just a few slides ago, I told you that all waves can be diffracted. Right. I just want you to keep that in the back of your mind, just for the next few minutes. So going back to the original thing of diffraction of waves, right? So this is what a diffraction of wave looks like. So we have some setup that looks like this. We have water wave, any wave going like this. When it hits the barrier, it sort of spreads out in this sort of like Wi-Fi shape, right? So that's what's happening. So applying that same logic to this sort of setup. So instead of one slit, what's happened is we've made two slits. So essentially, you can imagine this looking something like this, right? So this is what our new setup looks like. So imagine that we have water waves. Water waves are coming like this. Water waves that are coming like this. And what's going to happen is when it hits the barriers, it's obviously going to diffract. Like we know that because these are water waves, and water, obviously, it's a wave. And what's going to happen is at this point, it's going to diffract. We know that because when a wave hits a gap, it's going to diffract, right? We know that. When it hits the second gap, the same thing is going to happen because it's a wave hitting a gap, and when that happens, it's going to diffract. And you sort of get this to these two Wi-Fi shapes. Cool. So what this guy, his name is Young, I think it's Thomas Young. He made this experiment. So what he thought, because this was during the time where it was thought that light is a particle. Light is a particle. That's what a lot of people believed. And Thomas Young also believed that. So what he wanted to do, he wanted to make this experiment to disprove that light is a wave. And essentially, he made two slits, really, really small slits, and he shot a light through it. And the theory was that if light is a particle, this is what you're going to see, right? So you can, instead of a particle, you can imagine light to be I don't know, some tennis ball, right? And these slits to be a door. If you throw a tennis ball through a door, obviously it's not going to diffract, right? It's going to go straight through the door. It's going to go, oh yeah, you have some door, you throw the tennis ball, it's going to go straight through. That seems like common sense. And then that's what people thought. They thought that since light is a wave, when the light passes through the slit, it's just going to go straight through, and what you're going to see on the edge or like on the wall is this, right? So you can imagine like we have these tennis balls going through this one window, and we have tennis balls going through this other window, and these tennis balls keep going, and they hit here, and the tennis balls from here, they go there, right? That seems like it makes sense, right? But the problem was that's not what happened. So this is what was expected, right? If light was a particle, it's not a particle. Light was a particle. This is what you would see, right? And again, it makes sense. Like you're throwing a tennis ball through a door, and that's what you're going to see. But that's not what happened. What Thomas Young saw, this is what he saw. So again, this is what we expected, but this is what he saw. So essentially, there's a bunch of like spaghetti sticks of black and white. So if you assume that, let's just assume that this is white light. The white light hits the barrier, and what's going to happen is there's going to be like sort of sections of white light, and there's going to be sections of darkness. There's going to be sections of white and darkness. And the question is, like, why does this happen? Like, how did this happen? This because this is what was expected, and then why does this happen? Um, so yeah, so this sort of phenomena was described, um, was explained by light being a wave. So essentially, what happened was, you have light that's traveling through the waves, traveling through the gap, and this light is diffracting. Um, this light is diffracting. So you imagine that this is all the light waves, and light waves sort of diffract. And what happens is, if you combine the two, so like this is what we see with a single split. If you were to do a double split, right, you can sort of imagine this duplicated down here. So if this is the same wave, you're going to get something. You're going to get this, because again, it's a double split experiment. It's two. There's 2 points of diffraction. And what happens is, these two waves, they are going to form constructive and deconstructive interference when they reach the wall. So imagine if this is our wall. Yeah, on the wall they're going to form constructive and deconstructive interference. And so what you end up getting is something that looks like this. So imagine that, like you can imagine that. Sorry. Well, let's imagine that this is our wall, and let's say this is the center of the wall. I'll just do it again. So imagine this is our wall. This is the center of a wall, and so this is what Thomas Young saw. So in the middle, you would see a bright light, and next to it, you would see like a dark band. You imagine that's filled out. I just can't be bothered doing it now. And then after that, what you would see, he would see another bright band, and then next to that, he would see a dark band. And then again, he would see another. You'll see a white band. You see a white band, and then the same thing on the left-hand side. You'll see a white band and a dark band. And then this is what he saw. He saw this sort of zebra pattern. And this zebra pattern is what we call an interference pattern. And so what happened? So what happened was, so these are two splits, right? The light waves have diffracted, and they've sort of spread out. And they spread out at this position and spread out at this slit. And what happens is when they reach the wall, so I'm just going to, just for reference, I'm going to say this is the center. This is D1, so dark 1, dark 2. This is our dark 2, sorry, dark 1, dark 2, dark 1, dark 1. This is our dark 2, and this is our dark 3. And the middle, we have light 1, light 2, light 2, light 2. So this is our center. So next to the center, we have 2 dark patches, and then next to that, we have 2 light patches, and then 2 dark patches, and then light patches. So what's happened is that in the center, we have something called antinodal lines. Antinodes basically is just a fancy word to say constructive. Yeah, antinodal lines, constructive lines. But in this scenario, we like to use the words of antinode and nodes. Yeah, so in the middle, we have constructive interference, or antinodes. Next to that, so this is our center, right? And next to that, we have 2 dark patches. So we have dark 1 and dark 2. And this is our dark 1. Sorry. This is a dark 1, and we have like another dark 1 next to it. After that, so this is a dark 1, this is a dark 1, and next to that, we have another patch of bright light. And this bright light, we can call this as L1, L1. And then that pattern just goes on so forth. So after this light patch, we have another dark patch. And this sort of pattern just keeps going across. Yeah, so antinode is constructive interference, and nodal lines is what happens when we have deconstructive interference. It's a bit confusing to remember the two, but the one way I used to think about it is nodal lines. So nodal lines, no, you have nodal lines, and you have no at the front, no meaning no, and so nodal lines means no light, and an antinode would just be the opposite, so light, or actually having light, not darkness. And yeah, so this is essentially what happened. And so what that proves definitely that light is a wave. And because remember what I told you before, that all waves can diffract. So all waves can diffract, right? So if what Thomas Young showed, or what he proved, was that light is in fact diffracting. It's showing a diffraction pattern. And since only waves can diffract, light therefore must be a wave. And so yeah, he essentially proved that light is a wave. Why? Because light diffracts, and diffraction is a wave-like property. Yeah, so essentially, light's diffracting, and only thing that can diffract are waves. Therefore, light is waves, and that's pretty much what he proved. If you're answering a question, the most common question with this is something along the lines of what does Thomas Young's experiment show about the wave-like nature of light? And then you would say something along the lines of Thomas Young's experiment shows that light is diffracting, and diffraction is something that is a wave-like property. Yeah, and you talk about his results in the experiment, showing that his experiment showed that light was diffracting, and it created an interference pattern with nodes and antinodes, which basically means that a light is diffracting and diffraction is wave-like property, so light is a wave. You'll say something along those lines. If you want, you can actually write that down on your cheat sheet, something like that, but obviously a better version of that, and you'd probably just copy paste it. Hopefully that should be fine. Because again, those types of questions, when you start doing exam preparation, you'll realize that those type of questions are very, very common. Yeah, so what Thomas Young, the next thing he found was that the intensity of the light is greatest at the center, and it gets dimmer and dimmer as you move out. So going back to this diagram, so what he saw that the center of, so this is our center, so in between the two gaps, the center is always the brightest, and as you move out from the center, the brightness of the bright bands start to decrease. Yeah, that's one thing he found. The second thing he found was that the fringes, or the fringe is another word for bands. So this is one fringe, this is another fringe, this is another fringe. The fringes were equally spread out. And what he found, so what he found was that you can get this formula, where x is equal to wavelength times length divided by distance. So what this tells us is wavelength is the wavelength of light, distance is the gap between the two slits, and length is the distance from the apparatus to the wall. And all of this will give you a distance of x. And what x is basically distance between two light bands or two dark bands. All right, so going back to our diagram before, so again, so let's say this is our center. This is our dark band. Then we have a light band next to it, and then another dark band, and another dark band, or in other words, fringes. And so the distance between uh, between sorry between one bright band and another bright band, so this distance is equal to x, and the distance from one dark band to another dark band is also x. And essentially, it's the same distance because the size of the fringes, oh, I didn't draw them properly, but in actuality, the size of the fringes are the exact same. So the distance between here and here, and the distance between here and here is the exact same. And that distance is given by x. Yeah, so again, if I drew them properly, the spaces between dark and light should be even. And this formula, again, is on your formula sheet, and this is how you would use it. Cool. So, right, so we know that there's bright bands and the dark bands, right? But why does that actually happen? Like, why are we getting bright bands in the middle? But why are we getting bright bands in the middle, but not dark bands? Like, why are we getting dark bands here but not light? So the reason why is because of something called path difference. So going back to what we did like at the start of the lesson with superposition. So it's basically that. So if you imagine we have these two waves, right? And if these two waves are traveling together, we say that these two waves are in phase. Reason why they're in phase is because one, they have the same amplitude, they have the same wavelength, and it's sort of the same wave traveling together, right? So yeah, so this wave and this wave are the same wave, they're just traveling together. And if these two waves meet, they're going to constructively interfere. And we know that because I'll just draw out this wave. If these two waves are traveling together, right, it will look something like this, right? And since these are two different waves, the amplitude is going to add up, and you're going to end up with a wave that's about double the size. Cool. Yeah, hopefully that's pretty straightforward. But here's the thing. So if I take this green wave and I move it to the right by one wavelength, and so one wavelength is the distance from here to here. So that's one wavelength. If I move this green wave to the right by one wavelength, what do you think is going to happen? So if I move this by one wavelength, and if it loads, yeah, cool. What you see, well, if I drew it properly, but what you see, it's the exact same wave, right? It's the same situation from back there. It just moved one wavelength across. And because it's moved one wavelength across, and it's the same wave, these two waves they're still going to constructively interfere. Why? Because again, it's the same wave. They're traveling in phase. They're traveling together. So these two waves, they're going to constructively interfere, and you're going to get a bigger wave. Cool. Now what happens is if we move the wave by another wavelength. So this is another wavelength, and let's move the green wave by another wavelength. So let's move it down here. Again, since it's the same wave, they're traveling together, they're going to constructively interfere, and they're still going to constructively interfere. And if you move it another wavelength, so if I draw another wavelength, that's one wavelength. If I move the wave by another wavelength, it's still going to constructively interfere. Yeah, just a quick aside that this purple line, that purple line is going on forever. So you can just imagine that this line is going here, it's going here, it just keeps going. Same with the green wavelength. So that wavelength it keeps going on forever. But the thing is, it's still going to constructively interfere because it's the same wave. They're traveling together. And so what we say is that if you have two waves and they have been translated by n wavelengths, where n is a whole number, they are still going to constructively interfere. Because again, we showed this before, when we moved the wave by one wavelength, and when we moved it by another wavelength and another wavelength, it's still constructively interfering. Yeah, so if we move the wavelength by a whole wavelength, move the wave by a whole wavelength, it's still going to constructively interfere. Okay, now we're going to do something slightly different. We have this wave. I'll draw it out properly this time. Cool. We have these two waves traveling together, and they're constructively interfering. Cool. Now let's move the wavelength by half a wavelength. So this is the distance of half a wavelength. And let's see what happens if we move the green wave by half a wavelength. You get this. And the thing is, if you add these two waves together, right, these two waves are deconstructively interfering. Because if you add the amplitudes is going to add up to 0. And what you're going to end up with, a flat line. And the same thing happens if I move the wavelength by another wavelength. So we moved it by half a wavelength. Now we're moving it a full wavelength. So this is half a wavelength. This is half a wavelength. This is then 3/3. Sorry, 3/2 wavelengths. So if I move the green wave by another whole wavelength to here, again, it's the same thing. It's deconstructively interfering, and we're going to be left with a flat line. And again, the same thing happens with the constructive. If we keep moving it by a whole wavelength, we're going to end up with the same scenario of deconstructive interference. Yeah, so when this happens, we say that the waves are out of phase. You can sort of think of phase as like out of sync. So before, since the waves were going sort of in sync, it creates constructive interference. But since these two waves, they're out of sync by half a wavelength, it creates deconstructive interference. Yeah, and essentially every time we move a wavelength by n minus a half wavelength, it's creating deconstructive interference. So when we moved it by half a wavelength, that created deconstructive. When we moved it by 3/2 wavelength, again, that was deconstructive. If we were to continue the pattern, then 5/2 wavelengths is also deconstructive, and so on and so forth. And it's given by n minus a half. But the thing is, why am I going through all of this, right? It's because of this, something called path difference. And essentially, path difference is the distance from the wave or the wave source to some point. It's given by this formula. So S1 minus S2, where S1 and S2 is the distance the waves travel. So S1, the distance S1 travels, S2 is the distance S2 travels. And just looking at this graphically, S2 is obviously going to travel a longer distance than S1. And then the distance, the extra distance that S2 has to travel is given by this formula. So essentially you're just subtracting distances. So let's say this travels 5 meters, this travels 7 meters. The path difference would then be, path difference is equal to 5 minus 7, which gives us -2. And because we're taking the modulus of it, it's just 2. And if anyone's not doing spec, modulus just means just take the value. So if it's a negative number, just take the number that's there. Yeah, so the path difference is 2. Essentially what we're saying is the second wave has to travel an extra 2 meters than the first wave. That's all that we're saying. So here's the thing. In this scenario, if we were to calculate, let's say the wavelength of this wave is, let's say it's some water wave, and the wavelength is 2 meters. What is the path difference between these two waves to this position? The path difference here is actually 0, because this P is at the center of the two splits. So like our P would be like it's in the middle of the two splits. Because it's in the middle, S1 and S2 are traveling the same distance. So if they're traveling the same distance, the path difference is 0. So let's just say S1 travels 10 meters, S2 travels 10 meters, 10 minus 10 is 0. The path difference is equal to 0. And because the path difference is 0, the waves are going to arrive in phase and constructive interference will occur. But let's see what happens if we have some different scenario. Again, let's say the wavelength is 2 meters. Wavelength is equal to 2 meters. Let's say that S2 travels, so this is S2, so this is our S2 wave, this is our S1 wave. Let's say S2 travels 8 meters and S1 travels 4 meters. The path difference, so how much extra did the wave 2 have to travel? So the path difference is given by 8 minus 4, which is just 4 meters. So S2 had to travel an extra 4 meters. What does this mean? So you can sort of imagine this as like, so I'll do it in different colors. So let's say this is S1. Yeah, we'll just say, let's say this is S1. And we'll say this one is S2. So this is S1, S1, S2. So wave 1 and wave 2. What's happened is that wave 2 has had to travel an extra 4 meters. So since we said the wavelength is 4, if the wave has to travel an extra 4 meters, we are shifting the red wave to the right by 4 meters. Or essentially, we're shifting it to the right by 2 wavelengths. So this is 1 wavelength. And that's what happens when you shift the wave by 1 wavelength. And a second wavelength, we're going to end up here. And you can see these 2 waves are going to constructively interfere. They're going to constructively interfere because even though the second wave is 4 meters short, or it has to travel 4 meters longer, the 2 waves are still in phase. They're still in sync. And because they're still in sync, they will still constructively interfere. And because they're constructively interfering, we're going to get a bright spot. Hopefully that makes sense. So again, since we said the wavelength is 2, from here to here, that's 2 meters. And from here to here, that's 2 meters. And since the secondary wave is travels 4 meters longer, the secondary wave has to be shifted by 4 meters. And when that happens, you get this, which is still constructively interfering. And essentially, you end up with this formula, which is path difference is equal to n times wavelength. So if the path difference is a whole number multiple of the wavelength, you're going to get constructive interference. Because in this case, we had a path difference of 4, or we had a wavelength of 2, which gives us an n value of n is equal to 2. And because n is a whole number, n is a whole number, we're going to get constructive interference. Cool. Yeah, hopefully that's making sense. If you have any questions so far, yeah, put them down. The second thing that can happen is if we have deconstructive interference. Cool. So again, let's say our wavelength is 2 meters. Our wavelength is equal to 2 meters. Let's say S1 has to travel 5 meters. And let's say our S2 has to travel 8 meters. Again, I think you can see where this is going. So the path difference is essentially this number minus this number. So our path difference is equal to 3. And so I'll just quickly draw out So these are our two waves traveling. We have a path difference of 3. So the red wave, you know what, just for the sake of argument, I'll just say it's traveling, this is a distance of 6, just to keep in sync with the slide. We'll say we have a path difference of 1, because 6 minus 5 is 1, and yeah, cool, everything else is still the same. Yeah, so this is our red wave, the secondary wave, and the blue wave underneath is our S1. And because we have a path difference of 1, and the wavelength of a singular wave is 2, the red wave gets shifted by half a wavelength. So our red wave ends up being like this. And again, because you have positive, negatives, this thing is going to cancel out, and you're going to get 0, or you're going to get a deconstructive interference. And the formula for this one is path difference is equal to n minus a half. And again, that makes sense because we got a path difference of 1. We've got a path difference of 1, n minus half times the wavelength, which is 2. And then you get half is equal to n minus half, n is equal to 1. And for this to be true, n has to be a whole number integer. And since we show that n is equal to 1, and since this is half a wavelength out of phase, or half a wavelength out of sync, it's half a wavelength out of phase, or half a wavelength out of sync, it's going to deconstructively interfere. And the same thing is going to happen if we have 3-on-2 wavelength or 5-on-2 wavelength. It's the same thing. And yeah, so this basically sums up everything about path differences. So path difference, again, is the distance between S1 and S2, depending on how much longer one of the waves had to travel. Constructive interference will occur if the path difference is a whole number multiplied by a wavelength, well, by the wavelength of the light or the wave. And deconstructive interference is going to occur when the path difference is n minus a half times the wavelength. Yeah, so the thing is, his two formulas about constructive and deconstructive interference, they work with all sorts of waves. It works with every wave. And the thing is, you can do the same sort of experiment, but instead of using light, you can use speakers. And so if you have two identical speakers set up, playing the same sound, you're going to see the same sort of effect. So you can imagine we have these two speakers, and in the middle, you're going to have some really bright, or you're going to have some really loud music. But if you move to the next sort of fringe, it's going to be very quiet. And then the next fringe after that is going to be loud. And that that sort of pattern is going to keep continuing. And again, like was said before, the intensity of the sound will decrease as you move further out from the center. Cool. And yeah, so just to quickly sum up, what Thomas Young showed is that light. He showed that the light is diffracting, and light's diffracting, and when light diffracts, it's going to create positions of constructive and deconstructive interference, which again is a wave-like property. So this is a wave-like property. Cool. Yeah, so since he showed that light is able to diffract, that pretty much proves wholeheartedly that light is actually a wave. And with that, that was pretty much conclusive evidence that light is a wave. And yeah, just a quick note, when you're answering questions about Thomas Young, you want to be talking about interference patterns and constructive and deconstructive interference, because interference patterns and these constructive and deconstructive, they prove that light is actually diffracting. And if light is diffracting, then it has to be these things show that light is diffracting. And if light is diffracting, then it has to be a wave. And essentially, that's how you would answer these worded questions.